Here I have drawn our convex mirror with its center and focal point, and I've put our object over here. Now let's draw in our three principal rays and see if we can figure out if an image is formed or not. The first ray, and again I'll do the first one in blue, in parallel. So from our object we draw in a ray parallel to the principal axis, and again put a little arrowhead on it to indicate that it's going in toward the mirror, and then out from the focus. So we want to draw a reflected ray from the focus. It's then going to go up in that direction. And again, draw in a tab on the reflected ray indicating it's going up that way. Second ray, in toward the focus. So from our object, we draw in a ray toward the focus. And draw in our arrow, and then out parallel. So drawing this back out, reflected, parallel, this way. And again indicate the direction of the reflected ray. Our third ray is then in toward the center. So from our object in toward the center. And then what does it do? It goes back out on top of itself. There we go. What are our three reflected rays doing? Here's one, here's two, here's three. Do they cross each other? They do not. They do not physically cross. What do we not have in that case? We do not have a real image. However, let's notice, if we were to trace these reflected rays back, we notice that the reflected rays seem to come from the same point back here. Let's draw them all back. Now, we're going to draw dotted lines to draw them back. Anytime you draw a line that is not a physical ray, make sure you dot that line. Only physical rays get solid lines. Anything that's not a physical ray, make sure you draw it as a dotted line. So I'm going to draw this reflected blue ray back toward the focal point. I'm going to dot that. I'm going to draw the reflected green ray back toward the, back parallel. And I'm going to draw the reflected red ray back toward the center. And what do we notice? They all appear to come from the same point. They all appear to come from this point back here. We have a situation very much like what happened with the flat mirror last time, where the reflected rays from the object appeared to come from the image that was behind the mirror. So if you were standing in front of the mirror, you would see the image. It appeared to be behind the mirror. Very, very good. So in this case, the image appears to be behind the mirror. The rays do not physically cross, so it's not a real image. So what kind of an image is it? It is a virtual image. So we can draw that in. Again, the point where the rays seem to come from, that is the tip of the image, the bottom of the image, the base of the image on the principal axis. So we connect that point to the principal axis and then put our arrowhead up at the point, and there is our image. Let's label that as our image there. Very good. It is a virtual image. We can see that. Is it upright or inverted? Well, in this case, we see it has the same orientation as the object, so it is upright. What's the magnification? Well, let's estimate that. Here's the size. We'll come over here, say 1, 2, 3, 4, maybe a fourth. Let's estimate maybe a fourth, something like that. So we'll say magnification is approximately 1/4. Is it positive or negative? Remember, if it's upright, it's got to be positive. So the magnification is positive. Very, very good. The fact is that we can use the same mirror equation and equation for the magnification and apply that for a convex lens. There's only one difference, and that is, with a convex lens, we think of the radius as negative. The radius of the mirror is a negative quantity. So let's just pick some nice round numbers and stick in here. What shall we say? Shall we say the radius in this case, we'll call this, say, -4 centimeters. The focal length, again, which is 1/2 of the radius, will be -2 centimeters. Very important point. What does this mean? The focal length for a convex mirror is negative. What's the object distance then in this case? The object distance would be, well, if this is 4, the way I drew it, the object distance is 8. So we'll say the object distance is 8 centimeters. Great. Let's stick these values into the mirror equation and the definition for the magnification and see what we get in this case. Putting these numbers into our mirror equation, again, we have 1/do plus 1/di equals 1/f. Solving for di, we have 1/di equals 1/f minus 1/do, which is 1/f is -2 centimeters minus 1/do. Do was 8 centimeters. What do we get? We have -1/2 or -4/8 minus 1/8. That's -5/8. That's 1/di. So di is 1 over that. 8/5 negative, which is -1.60 centimeters. Well, let's take a look at our diagram and see how that fits. First, negative image distance. What does that tell us? A negative image distance tells us our image must be virtual. Well, that's exactly what we found, a virtual image. What about the 1.6? Well, let's see. If this is 4 and that's 2, 1 centimeter would be about here, and that looks like it's a little bit past halfway. Well, that looks like about 1.6, so that's pretty good. Our diagram seems to show that the image distance is 1.6 centimeters, and it's negative because it's virtual, so -1.60 centimeters. Very good. What about the magnification? The magnification is -di/do, or di is -1.60 centimeters over do, which is 8. Negative and a negative gives us a positive magnification, or positive 0.200. The magnification is positive, so what does that tell us? A positive magnification means the image is upright, and that's exactly what we found. It's upright. We get a value of 0.2, which is 1/5, while we estimated it to be about 1/4. So that was pretty close. It's maybe a little bit less than 1/4. Turns out to be 1/5. Very, very good. Couple examples of these that are very easy, like I mentioned before, is with a spoon, a shiny spoon if you could find one. Notice, first of all, that if you look on the, let's say the concave side first, if you look at yourself, you'll notice that you appear to be upside down. In other words, inverted, and that's what we found. The image for a concave mirror, if you're outside the focal point, which you probably are with the mirror unless you're holding it up like this, your image will be inverted, and you can see yourself as being upside down. If you flip it around and look at the back side, the convex side, you'll notice that your image is right side up. It's upright, and that's what we found for the convex side. Very, very good. So you can actually verify that if you just can find yourself a nice shiny spoon. One thing I want to mention that talked about before, and I want to go over this just a little bit, and that is, we have made this approximation that all of these rays are close to the principal axis. What if they are not close to the principal axis? I have a diagram I want us to take a look at that shows what the rays look like if we were to draw all of these rays in coming through the focal point. Let's just take a look at that. So here's the diagram, and all of these rays have been drawn as though they were to reflect off the mirror and pass through the focal point. You'll notice that these rays here, close to the principal axis, look like they have an equal angle of reflection, equal angle of incidence and reflection. However, these rays up here, away from the principal axis, they definitely look like they do not have an equal angle of incidence and reflection. You can look at the angle in between, say, the incident ray in the mirror and the reflected ray in the mirror, and those obviously are not the same angle. So these are definitely not equal angle of incidence and reflection. What does this mean? It means that it's only the rays that are close to the principal axis that will actually reflect through the focal point. Any rays that are too far from the principal axis will not reflect through the focal point. Very good. Well, what kind of an effect does that have? If you actually had a spherical mirror and you were to use all of the rays coming in, well, that means that all of the rays will not focus at the same point. All of the incoming rays would, well, let me redraw a concave mirror just for a second, and we'll take a look at it. So what happens if all of the rays of a mirror are focused down? What happens? If we actually have a spherical mirror, then not all of those rays are going to reflect to the same point. So here I've drawn a concave mirror, and all of the rays near the center, near the principal axis, will reflect back very close to the focal point. However, rays that are too far from the principal axis will not reflect back to the same point. They will reflect back to a different point. That means if you are trying to make an image, your image will be a little out of focus. And the larger the mirror is, the further it is away from the principal axis, the more out of focus that image will be. Even if it's a very small mirror, it's going to be a little out of focus because all of the rays are not going to reflect to exactly the focal point, but only close to the focal point. This unfocusing of the image is what is called spherical aberration. When you have a spherical mirror, the image is not going to be exactly in focus. And that's what this refers to, the fact that the image is really not going to be perfectly focused. For most mirrors, if you have a mirror that's reflecting, say, one of those big traffic mirrors that's reflecting traffic around a corner or something like that, it's not so important. You don't really care whether the image of a car is perfectly in focus as long as you can tell that it's a car. However, what if you do really care that your image is in focus as absolutely perfect as possible? Well, you don't want to use a spherical mirror. For example, in astronomical telescopes, when it's very important that the image is as clear as possible, the shape that the mirror is made is actually a parabola. So something like y equals x squared, if you take that parabola and rotate it around on its axis, you get a curve, a three-dimensional curve, that's called a parabolic mirror. So mirrors that are actually used in telescopes are not spherical shape, they're parabolic shape. And that will actually take all the incoming rays, even rays that are far from the principal axis, and reflect them back to the same point, the focal point for the parabolic mirror. Excellent. Next time, we're going to move away from mirrors, and we're going to start talking about what happens when light actually goes into a material. It's not going to reflect, although we will see it will partially reflect. It's going to do something else, what we call refract. We'll take a look at that next time. Well, I hope this was interesting. I'll see you next time.